Okay, Mike, just pass it on over to Tim, and Tim can get started.
All right. There we go. Tim, you should have it.
Excellent. Thank you. Well, good afternoon, everybody. Just a brief introduction so that you know who's talking to you. My name is Tim Cresswell. I began my career long ago as an engineering graduate in the aerospace industry. Spent 13 years doing aircraft performance and mission proving until I eventually saw the light and transferred to Caterpillar in 1994. I'm an engine guy by heart. I've spent my career with Caterpillar developing, marketing, selling engines for industrial and power generation applications. My role at the moment is product definition, which essentially means blending the needs of the customers. I guess that's you guys, the regulators and our own business to ensure that we have the right products to sell, products that people want to buy. Mike, whilst we're on this slide, would you care just to introduce yourself as well, and I'll move on with the opening of the presentation.
Sure. My name is Mike Devine. I've been with Caterpillar for about 40 years and been working the last 25 dealing with electric power generation in gaseous fuel power generation. So I get an opportunity to work with dealers and users all over the world to find ways to use combined heat and power and gaseous fuel products to improve their life and better to improve their bottom line. So, Tim, thanks.
Okay, thanks, Mike. Mike and I intend to split the presentation into manageable sections, and we'll take a look at the proper agenda in a second. Power generation is a pretty broad topic, so before we dive down into our own little hobby areas or rabbit holes for today, we'd like to start with a few generalities about the industry. For example, we often like to get people to consider what they're trying to achieve from their power generation system. It may be obvious to some, but sometimes it raises some questions for other people. For emergency standby systems, it's likely that the operating hour expectations are pretty low for that sort of installation. An operator's focus is likely to be on reliability, dependability, the fast starting of the unit, and the rapid acceptance of loads, especially critical or life-critical loads, and overall low installation costs. Some of our customers have higher hour expectations and applications, and their focus of interest changes to the economics and the operating efficiency of the units, for example, fuel efficiency. Also, the suitability of the units for use in demand response or peak shaving contracts, and the overall transient load performance of the installation when it's facing widely varying loads. Increasingly low site emissions are becoming a very hot topic, especially in the United States. As we know, our planet is becoming somewhat more populated. We're building more towns, cities, and infrastructure with every passing second. And demand for energy, electricity in particular, whilst relatively stable in Europe and North America, is growing fast in the developing world. It's not quite exponential, but the population is growing, and with it, the demand for energy. And it's fair to say that as the decades roll by, and more of that energy demand is focused on electricity, which is where we come in, obviously. Now, with dependence on something, you naturally get a lack of tolerance for its absence. So when I was a child, a power cut meant that supper might be cold and there was a reasonable chance you'd fall over the dog in the darkness, and that was about it. Showing my age here. But today, grid instability can spread very rapidly, and a power outage will potentially see communications networks collapse. If data centers are impacted, we lose access to critical information, financial information, commercial information, security information, to say nothing of Twitter, Facebook, and Instagram. At the other end of the scale, of course, in your world of healthcare, there are life-critical services which have to be guaranteed. And again, that is the focus of today's discussion. So selection, capacity, backup, redundancy, dependability are now key words for all of us, particularly on the phone today. And of course, we have now, in the modern age, have a new requirement to cope with, one of sustainability, which we also would like to talk about today. How to produce more of what we want and less of what we don't want, using as little of our precious resources as possible. So we're talking about reducing emissions, increasing fuel efficiency, using different fuel types, but all the while guaranteeing access to electric power on which we depend. So, moving on to the agenda. I shall start off by discussing some of the emissions-related challenges facing diesel installations in the United States. I mentioned I was an engines guy. Principally, I am the diesel half of the equation. Mike, on the other hand, is very intimately connected with natural gas units. I shall hand over to Mike so that he can then take us through some of the mysteries of the natural gas generators and combined heat and power installations. At the end, we hope that you will have a good view of this, and we'll summarize it into an ideal combined solution for you. So, diesel generators. I think it's fair to say that these have long been considered the best choice for healthcare and for many other mission-critical standby applications. The reasons, of course, are pretty numerous. The outright track record of what is a very proven product in design terms, the high efficiency and the high power density of diesel fuel generators, leading to a low initial cost and lower weight per output. The rapid starting and rapid load acceptance characteristics of these units, and the fuel flexibility and portability of that fuel are just some of the reasons for diesel's enduring popularity. However, we now face unprecedented environmental sensitivities, even without the help of our colleagues in Volkswagen, and words such as sustainability and topics such as emissions regulations are now playing an increasing role in the decision-making process when it comes to choosing a power generation solution. The U.S. Environmental Protection Agency, or the EPA as we know them, has been regulating industrial diesel engines through a tiered structure of emissions limits for over 20 years. Regulation began with off-road and mobile machine engines in 1996, and it was not until 2006, some 10 years later, that the EPA got around to dealing with stationary engines, such as our standby power generation units. Permitted emissions levels have got lower and lower through a series of progressively stricter emissions tiers. And today we are in the era of what we call Tier 4 Final, which came into force in January of this year for the vast majority of stationary diesel engines. Tier 4 Final affects stationary diesel generators in the United States. It affects mobile diesel generators in the United States and Canada. And the principal impact of this Tier 4 was that the regulated emissions levels were reduced to such a level that it was no longer possible to address them merely with combustion technology. Exhaust after treatment is required, and we use happy acronyms SCR, DOC, DPF, meaning selective catalytic reduction, which addresses nitrous oxides emissions, diesel oxidation catalysts to address hydrocarbons and particulate matter, and diesel particulate filters for ultimate filtration of particulate matter. All these are now becoming a common part of the recipe of a modern Tier 4 certified diesel engine. Just to add complexity, the emission standards vary with the power category of the engine concerned, from the very smallest up to the very largest engines. And they are by and large now reliant upon the introduction of ultra-low sulfur diesel. That means diesel which contains less than 15 parts per million of sulfur. This is now the only real commercially available diesel fuel within the United States, and the after-treatment and engine systems rely upon it to deliver the desired emissions result. One of the impacts for engine manufacturers is that not only do we have to have an engine that meets a given limit and an after-treatment system that is capable of achieving those limits, but the two have to be certified together as a complete system. And this is an important part of the EPA's regulatory structure. They wish to ensure that not only do these emission solutions work in the laboratory, but they also continue to work in the real world. Part of the certification program is a demonstration that these engine and after-treatment systems will deliver a consistent result over the emissions useful life of the engine, some 8,000 hours of operation. The use of an SCR system to control NOx is a convenient solution for engine manufacturers and is very efficient. We have to recognize that it also comes with what is known as an inducement strategy, which we will talk about a little bit later on, which is of particular interest, I think, in the healthcare industry because it has some implications about the operations of the engine. The very largest engines, which are probably larger than we would need to talk about here, have their own unique certification standard, which is combined with the largest marine propulsion engines. So there's much talk of complexity and much talk of reducing emissions levels. But there is some good news, and that is that engines which meet the EPA's definition of emergency can avoid some of these Tier 4 complexities. There are a separate set of standards which are set out that these so-called emergency engines have to meet. Now, to help you visualize what this nightmare world that I'm describing in which engine manufacturers have to live, here is a handy little graphic. I think it's handy, you may disagree, to illustrate the point. What we have is engine power in brake kilowatts down the left-hand side, and you can see the different categories that the EPA are interested in regulating. There are some odd little numbers in there. And across the top, we have the years of introduction of the various different tier standards. The colors themselves, as we move left to right, represent tiers 1 through 2 through 3 to 4 interim and 4 final. And you can see there's a wide complexity and matrix of different dates and engine powers that we have to deal with. The numbers in the boxes within the chart reflect the regulated limits at each of the different tier standards, and the principal pollutants that people are concerned with are oxides of nitrogen, hydrocarbons, carbon monoxide, and particulate matter, and the values can be read in a clockwise manner in each of the cells. The point I was making earlier about separate standards for emergency engines can be seen on the right-hand edge of the chart, where some of the Tier 2 and Tier 3 standards continue on through the Tier 4 life cycle. So those emergency engines only have to conform to an earlier emission standard and don't have to bear the complexity of emissions after treatment. I guess it would be true to say that the chart probably doesn't end here, and I imagine the EPA in their wisdom will invent a Tier 4, a Tier 5, and a Tier 6, but hopefully Mike and I will both be long retired before that comes to pass. So, from a healthcare perspective, I think you will agree that the definition of what constitutes these emergency engines is probably pretty important. Emergency in the EPA's eyes effectively means that the engine should not be required to run except when the normal source of power fails. Once the normal source of power fails, and that could be a fault with an incoming substation to the site, or it could be a statewide blackout, once that happens, there is no limit to the actual time that those emergency engines can run. But for non-emergency purposes, such as maintenance and testing, there is a limit of 100 hours per year for operating, unless there is a local code or a regulation that mandates otherwise. And the operator is required to record all use and reference it to the engine hours meter. Now, there have been a number of adjustments, shall we say, to this definition of emergency, and EPA have listened to industry and listened to operators and tried to make it a little more flexible. And in 2010 and 2011, they proposed an allowance of some 50 hours a year as part of this 100 hours to cover non-emergency operation for circumstances such as storm avoidance, where you might wish to run a facility such as a data center on the generators if there is bad weather or severe weather approaching. In 2012, EPA came up with a further modification. They responded to industry concerns by modifying this definition yet again to allow a 100-hour per year allowance for demand response. That is, grid suppliers declaring that there is an instability in the grid or the likelihood of a brownout or an impending blackout, and requesting emergency generator owners to start their generators and take their facilities offline. EPA unfortunately found that this modification was short-lived. They faced a legal challenge and were forced to withdraw this demand response allowance. So although it was included briefly and then withdrawn again earlier this year, I included only to raise the awareness in your mind and to generate some understanding. First it was here and now it's not. EPA are going to generate a new proposal, we believe, in late 2015 or 2016 to cover demand response yet again, but for the time being, emergency engines may only be used for unlimited use in an emergency situation, 100 hours of maintenance and testing. Of that 100 hours, 50 hours may be used for non-emergency running, such as storm avoidance. So we receive a lot of questions about the different classifications of engines, both emergency and non-emergency. So I'd like to try and summarize some of the practical differences between emergency and Tier 4 certified or non-emergency engines. So starting on the left, we have the stationary emergency engines that we've just been discussing, which effectively are Tier 2 and Tier 3 certified or meet the standards associated with the old Tier 2 and Tier 3. They carry that basic stationary emergency certification to those levels, and they are legal only for use in emergency applications, as we've just described. So they can be used in stationary, emergency only, for up to 100 hours a year maintenance and testing, 50 hours a year of general use, which is out of the 100 hours a year of maintenance and testing, but for unlimited use during an emergency situation. Now, many times there is some confusion because local site permits dictate that even these emergency engines are fitted with after-treatment to control site emissions. So they can certainly be retrofitted with an after-treatment system, which may be SCR or may be a diesel particulate filter. This does not change their classification in the eyes of the EPA. They are still only certified and allowable for the same use as an unafter-treated stationary emergency engine. So it is not possible in this way to convert a stationary emergency engine with its restricted operating characteristics over to a Tier 4 certified unit. You put after treatment on, but it does not change the basis on which you are able to operate it. Just to compare the stationary emergency with the non-emergency or Tier 4 certified, as we've discussed, restricted operation on the left for stationary emergency. Stationary non-emergency or Tier 4 can be used for both stationary and non-road mobile applications. It's fully certified to the full Tier 4 limits. It's legal for use in emergency as well, but essentially it can be run for unlimited use in continuous or prime power applications. So that's 24/7, 365 availability of power for unlimited operating hours. The one important difference, which we touched on earlier, is the presence of what is called an SCR inducement strategy on these Tier 4 certified engines. So many potential owners think that a Tier 4 solution is a good idea. It will enable them operational flexibility and will enable them to be as clean as possible in their site operations. But the SCR inducement strategy perhaps just bears a little explanation. The inducement strategy is basically a reflection of EPA's concern that emissions control devices should work in a consistent and effective manner and should be maintained in good working order. So the inducement is designed to do just this. It's to induce the operator to keep the thing working. It's designed into all selective catalytic reduction systems that are used on large Tier 4 stationary generator engines. It is basically a system that will detect a fault in the emissions reduction system and provide visual warning or notification to the operator for a fault. The inducement part of it is that if the fault goes unresolved, the engine will derate or shut down unless action is taken. Now, there is a warning period before that shutdown or that derate occurs. For a generator, it will be a derate. It will not be a derate. It will be a shutdown. And there's roughly a 4-hour period as the engine notifies the operator and then counts down towards a shutdown. There are a number of things that can cause this inducement strategy to initiate, but basically it's around the diesel exhaust fluid level or quality or a malfunction of the selective catalytic system and its sensors. That's the NOx reduction system. Now, designed into this inducement strategy is what we call a self-heal loop, which allows the engine to work out that the fault has been repaired and is not going to reoccur, and the overall inducement process can stop and the engine can go back to normal operation. However, the engine will and control system will look for repeat occurrences, and if that same fault reoccurs within a 40-hour period of the self-healing or the fault correction, the inducement process will start again, and the inducement times will be even shorter. So it's important to understand with you and your life-critical installations that our Tier 4 certified unit, an unresolved fault with the after-treatment or the FCR system, will currently result in the unit shutting down after a 4-hour period. Now, there has been widespread objection to that from the industry as a whole. Emergency systems are there for just that. They're there for emergencies, and the last thing we need is unresolved issues. So already mobile emergency engines have an override facility to prevent inducement shutdown from occurring. So things such as fire trucks and ambulances and firefighting equipment, off-highway firefighting equipment such as bulldozers and track-type units already have an override system. And EPA are now working on a similar provision for stationary engines. So we anticipate that within the next 6 months there will be a provision for us to provide an override strategy. So if there is a genuine emergency and the units are running, if we have a fault on our SCR system, then the fault can be overridden and the unit continue to operate until the emergency period is over. So, to summarize what we've just discussed, we have stationary emergency engines, which can only be used for emergency applications, 100 hours of maintenance and testing, and 50 hours of general non-emergency use, such as storm avoidance. The 100 hours of demand response allowance has now been withdrawn, and the rule will be rewritten to reflect something new in the next 6 months. We also have Tier 4 certified engines, which were a legal requirement for non-emergency applications from the 1st of January 2015. These consist of a manufacturer-certified engine package and after treatment, and they are the only equipment legal for non-emergency applications. There is no regulatory way in which a stationary emergency engine can be converted into a Tier 4 final certified unit in the field. So you have to buy the one or the other and then use it as intended. On the other hand, natural gas engines, as we shall now learn from Mike, can meet all of the requirements for both emergency and non-emergency operation with much less emissions control complexity than diesels. They're also perfectly suitable for use in standby applications. So, Mike, let me pass the ball to you.
Okay.
And while we are passing, we do have one question that came up from Greg. Is there any regulation, standard, or best practice regarding frequency of diesel fuel polishing for emergency standby generators? Mike or Tim, did one of you want to field that before we get rolling into the second half?
I will have a go at it. There is no regulatory requirement for that, or at least not from the EPA's perspective. Good practice says that you should treat the fuel obviously in the tanks. You should keep the tanks full, and not have so much storage on site as it's going to sit there for extended periods of time without use. But there is no regulatory requirement from our perspective.
Also, the length of period of time that you would have that fuel stored without polishing, it really depends on how it's being stored and where it's at. The environment obviously makes a big difference in terms of contamination and what you would expect to get in there, how quickly moss and mold, that kind of stuff, can grow inside there. And so if you may end up having to do it more in the southern tier states than you would have northern tier states or something like that, but it's basically determined based on what your situation is in a local area. Okay, what I'd like to do is to have a little bit of a conversation about some of the differences between gas and diesel engines, or in this case, some of the similarities. From an electrical perspective, and I'm talking about generators themselves and the switchgear that would go in there, the generators that you would use on a gas engine are virtually identical to those generators that you would see on a diesel engine. From a manufacturing perspective, if I have a 2/3 pitch, if I have a given frame size on a generator, stacked lengths on rotors, they're literally the same between a gas and a diesel engine. As for switchgear, when you parallel them to a utility, to the grid, the volts and amps flow kind of the same way. You have the same types of devices. You have, if you're parallel to the grid, you may have draw breakers on both of them. All of the equipment that you would require to be able to parallel and to stay parallel and to protect both the grid and the generators will be the same between a gas and a diesel unit. As far as the mechanical side goes, both engines are 4-stroke cycle engines. The air intake systems are basically the same on all of those systems in that you're worried about controlling whatever is in that air, the contamination that could come in from airborne particulates, dust, dirt, whatever. And the same considerations that you would use on a diesel engine, you'd use on a gas engine. So if I required dust ejectors or dual filters on a diesel engine, I would require those same types of filters on the gas engine side. Also, in terms of restrictions, you have the same considerations. So as I'm worried about restricting the amount of air, the length of plenums that I can use to get air into the engines, you'll have the same restrictions on a gas engine that you would on a diesel engine. In terms of exhaust systems, again, it's very similar in nature. The designs in terms of sound attenuation, in terms of if I require a stainless steel skin on the muffler in a diesel engine application, I would require probably the same for the same reasons in a gas application. Again, restrictions becomes a part of that issue. So as I have restrictions that would be limiting the length of my runs and number of bends I can have in those runs, how I install those runs, you'll have similar situations between the gas and the diesels. And on the cooling systems, you'll again have that same situation, and that the purpose of the cooling system is to cool the engine and to keep it in an operational state. If I have a gas engine, I would expect that the aftercooler circuit will be larger. We'll kind of talk about why that is in a little bit. But basically it's because I have an air-fuel ratio that is going to be consistent with that gas engine, and so I would expect that the unit is going to have the same amount of heat rejection on a per unit basis all the time, whereas a diesel is basically limiting its power based on how much fuel it's putting in, still has excess air in there, so it can change the temperature at some point in time on a pretty regular basis. So the two engines have a lot of similarities. Where the differences come in is when we start talking about the ignition system and the fuel system. The ignition system on the diesel engine is a compression ignition, so I basically have air that is heated. As I compress it, it heats up, and then I will basically inject the diesel fuel, atomized diesel fuel, into that for ignition in that system. On a gaseous fuel system, I have an air and fuel ratio that comes into that mixture. That air and fuel ratio then helps determine what the emissions are going to look like on that engine, and as a result, you have that amount of air and fuel in there. The spark lights that off. You have a propagation of the flame front from basically from the spark plug to the cylinder walls, consuming all of that air and fuel in the engine. And that's basically how it's set up. On the fuel system, I have a direct injection system for the diesel. And on the gaseous fueled systems, I would have a carbureted system. Again, the big difference there. Why am I using gas generator sets, or why would you use one? Why would you want to consider that? First off, is we know the quality of power for all of our applications is growing and continues to grow. We want more reliability. We want all of our power systems to act as an infinite bus that has very little or no voltage frequency changes. And that whole situation continues and continues to grow globally. We look at gaseous fueled generation that meets the need. Most of these are from local emissions. The gas engines have the capability of going down to half a gram of NOx output without any emission control strategies on them at all. So they do, in fact, help quite a bit when it comes to emissions and emission control strategies. The gas infrastructure is growing, and particularly with the advent of the shale gas, we're seeing a lot more opportunities for gaseous fuels being distributed on a regular basis, and we don't see shortages near as much as we did back 10, 15 years ago, particularly during the winter months here in the States. We're also looking at meeting very high efficiency demands, and the gas generator sets do have that capability. They do support grid reliability. In fact, many of the utilities will use gas engines to meet their peaking needs through maybe upwards of 4,000 or 5,000 hours a year. Local site reliability is certainly there. Product support is there for many of these reciprocating engines, dealers and local folks that can take care of these engines in addition to the folks that you'll have on staff at the hospitals. From a power generation perspective, lower owning and operating costs is certainly there. When we look at maintenance on an engine, as an example, an oil change on a diesel engine is typically going to be in the 250 to 300 hour range, depending on the oxidation, nitration, and your power levels within that area for that engine. For a gas engine, it's not uncommon to be in the 2,000 hour range for an oil change. The life to top end on a diesel on a prime power application could be in the 8,000 to 10,000 hour range. On a gas engine, you could easily get into the 20,000 to 30,000 hour range. And for a major overhaul on a gas engine, you're commonly talking in terms of between 40,000 and 80,000 hours. So significantly longer life to overhaul, and a lot of that has to do with the type of fuel that we're dealing with. In a distillate fuel arena, you're basically taking that diesel fuel, you're atomizing it, you're having to change that in the cylinder basically to a gas so it can be combusted. And then what's left as either in the particulates or others can create carbon that will wear much more regularly. On a gaseous fueled engine, you've already into that gaseous fueled phase, so you don't have the carbon that's in there to wear on the internal components in the engine, allowing it to go a lot longer before overhaul or maintenance periods would occur. The engines are quite well suited for combined heat and power applications, and that is also because of the electrical efficiency. Many of the engines that we're talking about now for these prime power applications are in the 44–45% electrical efficiency range, which is really quite good and operates in very high efficiency operations. The low emissions capabilities kind of already talked about, but they do have the capabilities down into that half-gram range out of the engine directly, and that can be very useful in applications where you're in tight emission control areas. Local fuel storage is not required with the gas engines. Obviously, you're looking at a pipeline, and there have been studies that have been done by the Department of Energy recently that indicate that the availability of fuel and the reliability of the gaseous fueled systems are very much working in favor of very similar to what a local storage would be. So your folks having jurisdiction over the applications are oftentimes now, particularly on the East Coast and the South Coast, where they've had a lot of issues with diesel fuel and fuel storage. They're looking at gaseous fuels as in a similar way that they would with an on-site storage from a diesel fuel tank, in that that there are very few places on those lines that they can cause problems and have delays or have disruptions of supply. And so even if electricity on gas compression systems that would be electric are there, they all have gas backup systems with the gas engines, very gas engines we're talking about for your applications. So they're actually backing up the entire gas supply structure, which makes them to the point where they do not have problems with gas shutting down in many of these applications. Transient capabilities on gas engines over the years has been somewhat suspect in a lot of ways. Part of that has to do with the fact that no one's ever asked them, if you will, to pick up transient loads. What we're doing today is have engines that are being taught, if you will, how to pick up loads, how to manage those loads more effectively. And engines that will be coming out in this first quarter next year are certainly capable of the NFPA 110, Section 1, where you have the 10-second start and picking up of loads in some of those engines. So those type of things are now coming online in very short order. 30 seconds has been, for most engines under, say, 2.5–3 megawatts for gas engines, 30 seconds online has been possible for quite some time and continues to be so today. Engines, as a rule, are pretty tolerant to the ambient conditions that you can have. So whether it be higher temperatures or altitude and temperatures combined, they can be put together in such ways that they can take as much advantage as they can. The limitations being the amount of air that is available to go through the turbine machinery on the engine to be able to support the full rating of that engine. So the derate tends to be due to the temperature or the altitude with the lower density of air and the total volume of air that I get in through the turbine machinery on that engine. If we look at some of the differences between some of these, we've kind of mentioned some of these here. The diesel engines tend to be higher power density. That has to do, again, with that air-fuel ratio that you have on the gaseous fueled engine, and because the gas engines tend to be limited based on detonation and on air temperatures coming in. So the temperature in cylinder and your exhaust, the resulting exhaust gas temperatures certainly makes a difference in, it's kind of the design limit, if you will, on the engine. It's one of those limits. On a lean burn engine today, which basically is lean burn engine basically adds excess air into your intake system when it's mixing with the fuel so that you still have the same amount of fuel to make, say, 1,000 kilowatts, and the stoichiometric level, which is basically the amount of air required to mix with that fuel to consume 100% of that air and fuel to create basically water and CO as your byproduct from combustion. But if you put excess air in there, what that effectively does is it lowers the average cylinder temperature. Nitrous oxides, by definition, are created basically in heat over time, so the higher the temperature in your exhaust and the longer that your exhaust is exposed to those temperatures, the more nitrous oxides you'll create. And as a result, you can lower your nitrous oxides by having these additional, the additional air in cylinder. So as a result, a lower power density is there on the gas engines as it is on the diesel, whereas the diesel, you're basically just adding enough fuel to create the power you need, but you still have a lot of excess air already in there. And so the gas engines historically been challenged by that. Initial cost-wise, diesel engines are basically at probably a 20 to 30% lower first cost on basis than what the natural gas would be. That's in a Tier 2 situation. If I have the total Tier 4 package, including the SCRs on the engine, the gas and diesel engines tend to be about the same cost under those circumstances. We see diesel engines running in typically lower hour applications, and here in the States that's primarily true just because the majority of them being either used for low hour peaking applications or for standby, and most of those are typically lower hour applications. The gas engines, because of their better fuel efficiency and their ability to have lower owning and operating costs, the owning costs or the maintenance costs, tend to have a lot higher hour of operation. So it's not uncommon for peaking engines on gas engines to go as high as 4,000 hours a year. And it's not uncommon for gas engines on a worldwide basis to have the ability to go over to have hours up to 8,000 hours and run quite well. The diesel engines historically have had the best starting and load acceptance. They've been in the NFPA 110 levels, 10 seconds starting, and be able to pick up block loads very effectively. The gas engines now are being taught, if you will, how to do that. And so we have gas engines that will be coming out in that 1,000 kW range here in the first of the year. That'll be capable of being fully started and able to pick up block loads within the 6.5 seconds, just like their diesel counterparts do, and to be able to do the block loads on the engines at pretty high loads levels. So emissions, again, are one of the considerations that a lot of people have been looking at for these applications, and the gas engines tend to do pretty well on the emission side. Let's go ahead and take a look at some of the standby and utility peaking type applications for these things. If I look at power supplies over the course of history, what most outages are talking in terms of seconds or microseconds even, and historically that's been the vast majority of those. What we do find, though, is when you have different types of challenges like we see today, whether it be from hurricanes, from fires, from ice storms, we see a lot of that in the Midwest and North, tornadoes, whatever, you can have some extended outages. And so a lot of these systems have been designed now to be able to deal with those longer periods of time. One other area that we're seeing now that needs to be really brought into consideration are sabotage areas. We've had recently transformer stations out in California, there have been people taking pot shots with 50 caliber rifles that tend to have some negative effects on some of the larger transformers they've got there. And in one case, it took up to 2.5 weeks to be able to replace those transformers just to get in the equipment and to trade it out. So we're finding that there are some of these sections that do have longer periods of time, and that if areas are susceptible, we need to be paying attention to that and watching for those situations. The gas engines today are basically designed into two separate areas. If you look at the left-hand side of that chart there, the units for healthcare for true standby operation, like an NFPA 110, 10 seconds starting, half PSI gas kind of ranges, are being designed at 2 grams NOx per brake horse per hour. That's the level that the EPA has set aside for those products, and that's what we're seeing that they're doing. On the load management side, those engines are designed to run at 100% load factors and run for up to 4,000, 5,000 hours a year. Those, on the other hand, though, instead of at 2 gram NOx, are limited at 1 gram NOx. So if they're over that 100 hours a year and it's out of that standby situation, you're going to be looking at 1 gram NOx performance on these engines. Again, it'll give you excellent fuel efficiency. As you lower the NOx requirements, you will have a negative effect on the amount of block load that you can pick up at one time on those engines, but they are very capable of doing that. The gas engines in the standby environment, the engine itself will be classified as a continuous operating engine. So even though it's technically in a standby application, because of the way you rate a gas engine with the limitations on detonation and on the temperature in the exhaust system, they are limited on exhaust and detonation, and so you do not reach a kilowatt level where you have a 10% overload. You're going to be at the maximum level on any standby engine that you have. Now, you may end up having, depending on the system you'd buy and look at, you may end up with a standby generator, which is meeting the same classifications that it does in the diesel world, where you'd have 130-degree temperaturized over 40-degree for that generator. But the engine itself will always be rated as a continuous engine, whether it's in standby or in a load management application for a gas engine. If I'm looking at the different types of engines and engine supplies, basically what we're talking about are emergency systems, which are those systems that are designed to protect people leaving a building. Those are the engines that meet basically the NFPA 110 requirements with under 10-second power starting and requirement. Those are typically on your elevators, your egress lighting, fire pumps, and fire detection systems for the most part. Those can be gas engines now as well, in that the gas engines will be able to pick up your emergency starting loads within that 10-second period, just as a diesel does. On your legally required systems, those are systems that are designed to aid the rescue workers and mandatory building functions, communications, ventilation, smoke removal equipment, that type of thing. They are by code designed to be on within 60 seconds. Most gas engines, again, under the, particularly under that 3,000 kW range, 2,500 kW range, can be online and be under load within that 60-second period of time. Up until recently, 4 or 5 years ago, we didn't see where a lot of them would allow these engines to be gas engines because of the fuel situation. But again, the Department of Defense studies that I mentioned before have found that there's a lot of good things about the natural gas engines and the amount of gas that's available. For example, when we had Hurricane Katrina, there were in the hospitals in New Orleans, there were 5 of them that had CHP systems. When the diesel fuel was not available to those generator sets, we found that the gas, even though the pipes were underwater, still was available to the generator sets there, and so they simply moved the emergency loads from the diesel units to the gas units. And so we're seeing that a lot of these folks having jurisdiction on these projects are now saying that they want to see some of the gas engines in these applications, and even if they're gas and diesel, so that they can have the dual fueling capability, dual engine capability, to be able to make sure and give them even a better chance of having these block loads and maintaining those loads. We also find that optional standby systems, which are basically undefined, gas engines have been used in these applications for many years, and so particularly like in hospitals, If you have the rest of your floors, or you have the nursing stations and other areas of the hospital that have historically not been required to be under either the legally required or emergency systems, the optional standby systems have been very plentiful and very useful in those applications. So why would we use natural gas in standby? The diesel fuel tends to be that weak link, and we talked about the fuel polishing and so on. That's all not necessary when you have the gas fuels. You have a high availability gas and a low risk of contamination in the gas as well. From an emissions perspective, the gas engines meet most all of the new source performance standby requirements. That's the 2-gram level. But in some areas where you have people that are requirements for higher levels of emissions, you can either do it with the engine with lower emission capabilities, again at the risk of being able to have that same load acceptance that you would. So the lower the NOx level, the lighter, the less fuel I have available to the engine immediately, and so that can and make it a little more challenging on some of your load acceptance requirements. But for true standby applications, a lot of these are working quite well. In the diesel fuel tanks, the code restrictions in many areas along the coastal areas or flooding areas, and it doesn't have to be coastal. If we look at the Mississippi and what happened there, what was it, 10 years ago, I guess, in Iowa and Missouri, where they had all the challenges with the flooding there as well. Many of those areas are restricting the amount of diesel fuel that can be located anywhere in those flood-prone areas, and there's no fuel polishing required. The application flexibility of fuel costs, if I'm looking at a 100-hour operation for a 1.5 megawatt system, you can have upwards of $34,000 fuel savings by having the gas engines operating during that time over what you would with diesel fuel. That's a gas at $4 per million BTU, and the diesel fuel at about $3.20 per gallon. So you can have a huge impact there. Also, there are many areas that are asking for demand response. This is one of those the diagrams out of California, where they're having a lot of the renewables that are coming in, and they're looking at a total load dropping during the day, and by that 2020, rather significantly, dropping from about 12 gigawatt load that would be during the standard daytime hours down into the 6 gigawatt range because of all the wind and renewable resource that we've come on photovoltaic. And then all of a sudden, toward the end of the day, when the sun goes down and the wind slows down, they're having to jump up into that 22 to 24 gigawatt range and doing it very quickly, and they're very concerned about how they're going to get there. Demand response is one of those opportunities, and with the equipment that's there, the demand response basically allows you to operate the engine, making sure that it's going to be functioning properly when you need it most during your standby outages. So it can be very beneficial toward long-term benefit on your engines. Load acceptance, the engines are, gas engines are now capable of picking up quite a bit of load. 25% block load is not uncommon on these, and load rejection as well. So we're able to do that. There's a number of different methods that we can do, and so we're finding that the gas engines can do that very effectively. So in these load applications for the load management, we're seeing that, again, they're designed at the 100% load factor. Upwards of 4,000 hours a year, again, are not uncommon, and 1 gram NOx would be the standard setting on those engines. For combined heat and power, basically what we're talking about is the simultaneous and sequential use of power and heat from the same source. So it's basically electric power coming out of the generator on that engine, and I'm using the heat coming out of primarily the jacket water and aftercooler, which are typically for engines under that 3,000 kW. Usually they're on the same circuit. So you can have that heat is available to you, and the exhaust heat is being right. Now, the numbers that you see on this chart is different for basically every engine and even every application. Just simply the difference between a 1 gram engine and a half gram engine will change the heat balance or the amount of heat going out each one of those components. So pay close attention as you start working with combined heat and power plants, and you're designing those systems to know what that engine needs to be doing and what the ratings and settings are going to be, so you have a good idea what that heat that is available to you is going to be and what you can use it for. Now, the heat can come in terms of hot water, it comes out in steam, and you're going to see most of those two applications in hospitals and healthcare facilities. You do have the availability of hot air, which can come off of the engine, and that could be just simply the radiator moving that air. But in most of your applications, my guess is you'll be in the hot water and the steam applications. You're taking the air and fuel coming into the engine. Basically what you're doing is you're taking electricity off of that engine. You also have the capability then of going into that jacket water system and being able to take heat out through a heat exchanger and running them through either feed water or heating for other purposes. Keep in mind that the cooling system there, that cooling water, the number one purpose of that is actually cooling the generator set. It is not the combined heat and power. So you need to pay attention to that very closely to make sure that the engine is being cooled at all times, because if the engine doesn't work, you won't have either power or heat. And so it doesn't make a whole lot of sense not to do that. You also have the capability of taking the heat off of the exhaust systems, which can be very beneficial to you as well. That's the highest quality of heat, and we'll see that here in just a moment. Traditionally, if I'm talking about just electric power loads, you're talking about electric and heat coming off of from typical utility sources, you would end up with quite a bit higher fuel usage than you would if you're in the cogeneration range. So that cogeneration, you can take both the electric and the heat off of those engines and use them, and can be very efficient in those operations. If I got my electric power, which you know you're going to have, the jacket water coming off of that is going to be somewhere between, typically it's going to be in that 195 to 210 range. There are some engines that are capable of higher systems so that you can take solid water off the engine, flash it to steam outside the engine, and use it there, 15 psi typically. The warm aftercooler water is lower quality, up into that 90 to 130 degree range, depending on the system, but oftentimes not used because it is such a low quality, but it is there if you can use it and it's available to you. What we do see is a lot of use out of the exhaust gas, and that's going to be for steam. Could use it for chilled water through absorption chillers, and can be very beneficial that way, along with the CO2 coming off the engine, and used in many different applications, and in healthcare facilities can be very beneficial. In the cogeneration process, we're talking about the heat exchanger for the hot water or steam. In a tri-generation application, you're talking about an absorption chiller that could be used to create chilled water, and the excess heat after that, which will be less than the total before, because I'm using some of that heat for the chiller. You do have access to that again for primarily hot water purposes. Now, on a typical system, it's not uncommon that you'll see the size here, and I'm showing this more for the benefit of getting kind of feel of the size of the units. Jacket water heat exchanger is that device that's off the front of the engine. It's a relatively small unit that does quite well in that application. Then you also have the muffler heat exchanger and exhaust after treatment if you require that. That would be in a muffler that could be set next to the unit. You also have applications where you can basically set those pieces anywhere around the unit. So if the muffler needs to be above the unit or to the side, or if you need to put them in series, that's not a problem. The key is trying to keep them as close to the engine as possible to be able to reduce restriction as well as to maximize your heat benefit. Now, the combined heat and power is an economic decision, and you're going to decide if I need it for the electric load, which most of the people here in the States will. You're going to want radiators and so on with those engines to be able to blow off heat if I'm not using the heat recovery. In some areas, you may require the heat as being your primary source. In those cases, you would not necessarily need to have a radiator for the engine, in that if you're not using your combined heat and power, if you're not using the heat, then you wouldn't be needing the generator sets either. But the key is, what's the value of the heat, and how much is the cost of retrieving that heat and distributing it to make sure that I've got something that makes economic sense. Here's an example of a system that happens to be in the 89% efficiency range. Notice again on that left picture that you have the system which has the heat exchanger. It's basically a plate and frame heat exchanger, which is taking the heat out of the jacket water system. This is another system where you're taking both the heat off of the engine as well as off of the muffler on the silencer that you see on the back on that lower picture. So it's basically acting as the muffler and as the heat recovery system on that engine. A lot of people are using these types of things. Here's a 72 megawatt plant for both hot water and absorption on a system, has over 100,000 hours on it, but it's being used in the AMD chip manufacturing facility. so that people who have very tight requirements on electricity and heat and power rely on these systems for their primary energy sources. And if you're looking to be a LEED certified facility, these systems can certainly be doing that with combined heat and power applications. Operation and maintenance is a real strong consideration because if you do not maintain these right, obviously they're going to be more prone to failure. And so if you're operating a combined heat and power system, you really need to have that tied together well. Load profiles are very important in that here you can kind of get an idea that the summer peak on this electric profile is the blue line on top. The red line down below is the heat, if you will, or the winter use of that load profile. If I'm not in conjunction, if it's not coincidental with the thermal load, which in this case is the hot water is up on top in the winter when the electric load was lowest. If they're not coincidental, you will have challenges with it. So you need to make sure that heat recovery is on a coincidental basis. Which combustion technology do you use? If I'm talking about 10 seconds starting, if I have large loads, it's not uncommon that diesels will be the unit of choice, particularly if they're in a true standby under 100 hours a year type of applications. For peaking, we see by far more applications with the gas engines. And if I'm using high power pressure steam, turbines like a Solar turbine can be very beneficial in here, and you combine that with the resource of a gas engine and diesel engine, and you can do some really good things with that. But hybrid systems, gas and diesels and turbines on systems are not at all uncommon. So here you can see where I've got a utility as the primary, I've got my diesel as a secondary, and you can have a tertiary feed, if you will, which is either going to be the gas engines or turbines or other source. All of those can be very beneficial for you. Maintenance considerations, I want to touch very quickly on it. If you don't maintain your systems, it's not going to work really well. The major reasons we see these units not operating is because the batteries are discharged. Can't tell you how many times we see the systems not in auto or you have bad or contaminated fuel. Let's skip through a couple of these real quick because I think we want to get to some questions here. The duration of the outage is really important to us. And so if you got like Ike and Sandy, both of those had 500–600 hours of service that was required. So what we're trying to do is do preventive maintenance on these systems, trying to make sure that they're right. And the key is that just because I'm in an emergency situation does not mean that I don't need to do maintenance. So if I'm in a 500-hour situation where I've got an outage and a diesel engine's there and it requires oil changes at 250 hours, you've got to find a way to do those oil changes, or the unit could fail while it's in service and standby. So make sure that you're working these systems so that they can be provided the services that they need in order to be able to run and run effectively. So make sure you have options in there for that type of system. That was kind of the quick view of the gas engine side of this. We want to go through some of the questions then?
Mike and Tim, do you guys have the questions? Do you see them popped up in the chat? Are there any that you want to go through and address?
We can. Are there some of these that you think are more important than others for your folks to answer here? We can answer all the questions and get them back to you so you can post them. We'd be glad to do that.
Yeah, I think that would probably work. We definitely don't want to, get cut off from everybody, and I know we are closing in right on 1 o'clock right now. So if you do have further questions, we do have the email address for Sharia posted so that you can send any questions, and we'll make sure that Tim and Mike will get back to you on those. But we want to thank everybody. First of all, especially thanks to Kat, to Michael and Tim for giving us an hour of your time. Thanks to everybody who has logged in. If you have any questions, we do have the email address posted for you here. And we hope that you've enjoyed what we've sent you for Engineering Week. We will be sending out a survey, like I mentioned earlier, so that you can give us a little bit of feedback. We want to make sure that we are giving you everything that you need and that we're giving you valuable resources. And then we will also, as Kevin just posted, if for some reason you missed part of this, or if you wanted to share this with somebody that you work with, this will be posted on the ASHE website in about 1 week. So with that, again, thanks to Michael and Tim. Thanks to everybody for dialing in and listening today. And we hope you all have a fantastic rest of your week. And we will talk to you very soon.